Okay, so we're going to be looking at a bit more logarithms and nonlinear data. We kind of looked at this a bit before when we were talking about these relationships that are in the form of y equals ab to the x, or y equals k x to the n, or ax to the n, this sort of thing. So what we're looking at today is effectively it's a chapter on the same topic but in one of the other textbooks, so it kind of makes sense that we're teaching it back to back in that way. So they will be quite similar, but there's a little bit of overlap, and then there's also a few things that perhaps we didn't quite see. I think in particular you'll get a few more practice questions specifically on the components of these coded equations. So treat it as a sort of review and a little bit of extra work to do on this topic, that topic being coded data and getting the line equations for the coded data. Just to get us into the swing of things, a question to think about here. So as you know, if you drop something from a height, it will take a certain amount of time before it reaches the ground. The relationship is not linear, so that I hope we know. If I double the height at which I drop something, it does not double the amount of time it takes to drop. So if it's not a linear relationship, what do you think the relationship might be? If you remember your mechanics, you might be able to derive it, or you could use a bit of intuition. And on top of that, before I reveal it to you, see if you can have a think about how might somebody who didn't know the mechanics of it estimate the equation that governs the relationship between the height and the time taken. Okay, so have a think about that. See if you can get the relationship, and then see if you can think about how you might do it experimentally. So pause now, and then once you think you're ready to hear the answer, you can unpause. Okay, so let's first find the actual answer, and we can do this because we know about mechanics. So we're going to use a bit of Suva actually. This isn't a mechanics lesson, but it is relevant for this particular question. So if we remember, we've got the equation S equals ut plus half at squared. Now in this case, S, that's the distance fallen, so really that's our capital H. U, in this instance, if I'm dropping something from a given height, we assume it starts from an initial speed of 0, so therefore ut disappears, so we're just left with h equals this thing. A is gravity, or to be more specific, not is gravity, but is acceleration due to gravity, which is g, and that's our relationship. So the height is proportional to t squared, or to put it another way, the time is proportional to the square root of the height. Okay, either one is acceptable. Okay, so that's if you knew about the mechanics. But of course, it's easy to forget that back in the day, if you're a physicist, you're trying to experimentally determine these properties that govern the universe, you might not necessarily know about S equals ut plus half at squared or something like this. But what you can do is assume that there might be a power relationship. So maybe you're thinking, okay, it's h is proportional to t. No, that doesn't work. Is it t cubed? Is it t squared? Is it t to the half? Is it some other power? And so then to answer this question, how could it be determined experimentally? What you could do is use coding, right? So if you know that h is equal to, in this case, let's not use a, that's a bit too ambiguous, let's use k. So let's say you know it's in this form, or you're assuming it might be in that form. Then you can do your coding, right? So you can say log h equals n of log kt equals n of log k plus log t, and so on. I won't finish it off now because we're going to look at that again in a moment. But the idea is to just remind you that this is partly what the point of all this coding and this linear encoding is. It's this idea that you may not know what a power actually is. You may not know that it's squared or cubed. But if you did some experiments and then logged all the data points, took the log of them, if you got a line, then you could consider the gradient and the intercept, and you would be able to determine what this k value is and what this n value is. Okay, so I suppose that, you know, at a more advanced level, if you're trying to do a bit of physics and trying to deduce a pattern, if you know roughly speaking what the pattern might be, you could then discover the constants by using this technique. Okay, I haven't finished this off properly now because I want to spend a bit more time on the actual examples, but that's the principle and a reminder of why we're actually doing this. Okay, let's continue. So this is completely a refresher. You've technically seen this, but I think it's nice to have it all in one image. So this is actually taken from the textbook, and I think it's a nice visualization. We've got two cases, so there's two of these images. This is the first, so I'm just going to have this one up on screen for a bit for you to sort of process. I'll just talk through it. We'll do an example for this case, and then we'll look at the second case, and we'll do one more example for that. When I say two cases, this being case one, meaning the type of equation we're talking about. So if you can see my pointer there, this is the case where we assume that a set of bivariate data is modeled with y equals ax to the n. And we don't know what n is, and we don't know what a is. An example of that being what we were just looking at on the first slide. So the working is done for us. Just as a reminder, let's just talk through this. If you have a non-linear relationship, y equals ax to the n, to convert that to a linear relationship, we're going to take logs of both sides. By default, let's say log base 10. So we get this. Then we use our log rules to split the log of a product into that. Then that n on x to the n goes outside the log, and we have this. And then after applying the log rules, we compare this equation to the common form of a straight line, y equals mx plus c, capitalized here to distinguish it from little y and little x. Log little y is big Y, log a is big C, n log x is mx. Specifically, little n is that big M, and log of little x is that big X there. Okay, and we align it in that way. And then this image here just shows you absolutely what's going on. So if you logged both sides of an equation of this form and then looked at the data, perhaps you did a PMCC to determine, yes, a linear regression is acceptable, and then you used your calculator to find the a and the b, right? The y equals ax plus b. In this context, the a will give you this capital M, and the b will give you this capital C. What you can then do is also here remind yourself what the meaning of each of these things is. So the gradient of the line is going to be that n power. So now you know what the power of n should be. And the y-intercept, that c, is the log of the little a. So if you then did 10 to the power of that c, that would tell you what this a value is meant to be, right? So this is not new. This is what we were talking about before, but I think this is nicely summarized in sort of one big picture. So it's worth taking notes on this, or at the very least having a copy of this for revision in your own terms, because I think it lays it out quite clearly how to work with this case. So let's look at an example of this particular case. So we've got a rank by size of the UK's largest cities and also their population. Right. London's ranked number 1 but has been excluded as an outlier. Of course London is an outlier. Right. Okay. Interesting. That's a bit of I'll just comment, that's a bit of an odd thing to try and correlate, because of course there will be a correlation between, right, there will be a correlation, okay, it's maybe not that odd. There'll certainly be correlation, right? If you say, right, on the one hand I've taken the rank of the population, and on the other hand I've got the actual population value, is there going to be correlation? I mean, there must be, right? Because the whole point is higher rank means more population, lower rank means lower population. So to just comment on what might initially seem weird, ultimately what this is doing is trying to figure out how quickly does it change. So when you go from the biggest city, say London, and then you go to the second biggest and third biggest, does it change steadily, or does it change exponentially or logarithmically? And if so, how quickly, right? So that's effectively what we're testing here. So really, there's only one variable of interest, it's population. But what we're doing is turning it into bivariate data by pairing each population with its rank. Okay. So I mean, the mathematics doesn't change, but just something to worth thinking about is that it might seem odd initially to just pair it up with the rank, but that's why we're doing it. Okay, so the relationship between rank and population can be modeled by the following formula. R equals A capital P to the N. So we want to figure out what this little a is, and we want to figure out what this little n is. Draw a table giving values of log r and log p to 2 decimal places. Plot a graph of log r against log p using the values from your table and draw a line of best fit. Use your graph to estimate the values of a and n to 2 significant figures. Okay. A and B are not particularly exciting, but we have to get them done. In terms of how you would actually answer this, I would not necessarily bother writing out the values at this stage if you just want to do a quick practice. Instead, and then likewise, drawing a line of best fit and then using the graph to estimate it. We're at the stage now where we don't need to do this. You don't need to arbitrarily draw a line of best fit. You can find the precise line of best fit, quote unquote, which in our case is this linear regression line, the one that minimizes the difference of the squares of the differences, right? The least squares regression, remember. So rather than doing it in the way it asks us to, by drawing a table and plotting a graph, let's see if we can find the value of a and n, but just by using the calculator. Okay, so really it's you doing this example, but I'll check that we end up getting the same numbers. Okay, so I'll grab my calculator now, and I'll fast forward time in a moment, but I'll grab my calculator and I'm going to enter the logarithm of each of these pairs. So log 2 against log a million, log 3 against log 30,000, and so on. Put that in the statistics table on your calculator, and let's see what value we get for the regression line, and we'll see if we agree. Okay, so you can pause now actually, see if you can get the two numbers, and then we'll see if we agree on our linear regression line. So just to clarify, we're going to find y equals a plus bx, and what are these? Okay, let's quickly try it. Okay, so I did it on the calculator. I typed it directly into the table, just wrote in log 2, log 3, log a million, log 30,000, so on. Didn't have to write anything down on paper. And I end up getting y equals a plus bx as being, in this case, 6.193 rounded, minus 0.666. x rounded. Yeah, and also the r was minus 0.996, so that's incredibly well correlated, right? That's extremely close to -1, indicating that this pattern I equals ap to the n is almost certainly the pattern that we want, and the values for a and n we're about to get are in fact going to be really good predictively. At the very least, anything near these two values, 2 and 6. So we've got to be a bit careful here because this little a is not the same as this little a here, right? So if you remember the table we just looked at, we were saying this is the intercept, that's the y-intercept, and this one here is the gradient. Okay, and you could rederive it, but if you go back to the meaning of each of these things, we had it in the table that the gradient corresponds to the n and the y-intercept corresponds to the log of little a, right? And again, don't get confused, this purple a is not the same as this black a over here, right? They're different a's. It's just unfortunate that the calculator uses a plus bx. So then we've basically got the following: n equals minus 0.666, that's done, and a is equal to 10 to the power of 6.193. So then I go to the calculator, I type in 10 to the power of 6.193, and I get about 1,560,000, if I can say it that way, which I can't really, about that, 1.56 million. So finally, that tells us what the actual relationship is, right? It's going to be R equals 1,560,000 times population to the power of minus 0.666. And there we have it. So you could, now you've got to be careful here. According to this rule, for instance, the rank 1 would be London, and that would indicate London has a population of 1.5 million, which it does not. I've just noticed one small error, I think. In my copy of the textbook, this says P equals AR to the N, and this image here, which is from a digital version, it's the other way around. So one of them is wrong. What makes sense? Yeah, this P and R should be the other way around. Because if the rank is 1, it's estimating a population of 1.5 million, which is not right for London because there's an outlier, but that's actually a meaningful value. Yeah, it should be the other way around. Everything else is all the same. But yeah, that makes far more sense. Given the rank, what is the population? Cool. All right. So that's it. That's the method. Let's take a look now at the second case. Okay, so case 2, I shouldn't need as long to talk through it. It's similar to the previous case, but just remember the subtle differences. The main big difference being that in the previous case, you have both x and y being coded with log, whereas in this case, only the y is coded with log and the x stays the same. Y equals a to b to the x, you log both sides, so always log both sides. Use your log rules to get this expression here, and now the x comes to the forefront, and now you've got, when you compare it to y equals mx plus c, you've got the following situation. log of little y is coded as big Y, and little x is just coded as big X and is not changed. And now, unlike before, the gradient is not our n value. In fact, there is no n in this case. Our gradient is going to be the log of the b, which is base. It's the base constant. And our intercept in this case is still the same. It's our log of this little a, which is this multiplier here. So in terms of what's the same and what's different, this bit's the same. The intercept is always log of a, but this part here and this part's the same. Y, capital Y is always little log of little y, but the gradient and the coding for x, this part here in the middle, is what's different. And if you can memorize the differences, then that's the key thing. So let's look at one example of using this. Okay, so we've got growth of a population of bacteria over t hours. So we've got t on the x-axis and p on the y, at least originally. This picture here is the coded version, presumably, because you've got log. The graph has represents the growth of a population of bacteria over t hours. Okay, I might disagree with that in a moment, but let's continue reading. The graph has a gradient of 0.6 and meets the vertical axis at 0, 2 as shown. A scientist suggests that this growth can be modelled by the equation p equals ab to the t, where a and b are constants to be found. Write down an equation for the line. Okay, so my comment here is that's phrased a bit weirdly. It says the graph, which is presumably this thing, represents the growth of a population of bacteria p over t hours. But if you look at the graph, it's labelled log p. Now that makes sense, because if it was labelled p, it wouldn't be a straight line, right? Because that relationship is not a straight line. So I think that English phrasing is a bit odd. But fortunately, they've labelled it correctly here, so we're going to go with what the graph shows. This is a graph of log p over t hours. And now let's use the information from this graph to deduce the equation for the line. So to do this, again, we refer back to the previous slide where we saw how we line up the line with the model. And the intercept, we note that this is log of little a. Okay, and then there's more information here. It meets gradient of 0.6. Okay, so the gradient is 0.6. And again, referring back to the previous slide, what did we know about the gradient? The gradient in this particular case, this particular model, tells me what log b is. So log b equals 0.6. Okay, so we've got log a is 2, log b is 0.6. Therefore, we have a is 10 to the power of 2 and b is 10 to the power of 0.6. So a comes out nicely as 100 and 10 to the 0.6 is approximately 3.981. So right, yeah, I'm doing part B here, which is far more sensible. Part A is sort of child's play. We know how to do that. Y equals mx plus c. So now that we have this a and b value, let's plug it in. So we've got capital P equals 100 times the base to the power of t. Okay, and then you've got your invisible times sign there. And that's it. We've created the model from being able to look at that straight line. Final question. Interpret the meaning of the constant a in this model. What is the significance of that number? What does 100 mean? And in this case, hopefully we get it. At time 0, P is equal to 100 times 3.981 to the 0, which is 1. So it's equal to 100. So the meaning is it's the initial population of bacteria. That's an easy one-marker question. which just gets you to acknowledge what the significance of these numbers actually is in terms of the reality of the situation. Okay, so it's just the initial value of whatever it is you're measuring is what that a constant refers to, because when you plug in t as 0, you just get a by itself. Cool, so that's it. So just try a few more questions now, really. You want to, I think it's good to get used to just being able to read off what these values are and how to interpret them, rather than having to rederive over and over again. So if you can start remembering that for that particular case, the gradient is log b, and for the other case, the gradient is whatever it may be, then you can start to answer these questions very quickly. And you don't have to rederive all of the steps that you've seen in the previous slides. Okay, so 4 questions total. There's just only enough space for 1 question on each of the 4 slides. I am going to just briefly explain for each question what parts you actually need to do and what parts you don't need to do, because I don't think you need to be, again, drawing graphs and plotting rough lines of best fit. You want to do it a more sensible way. So let's look at this question first. What do I actually want you to do? This one you can just do as it stands, no plotting or anything needed. It's just a simple check. So give this one a go. You can pause the video now and then check your answer. Okay, and then don't worry about the size and wordiness of the question. There's not that much to do here, I don't think. This law in itself, by the way, is really interesting. If you get time someday, go on Wikipedia and look up Zipf's law. It's very weird. So in terms of what I actually want you to do, copy and complete this table. That's optional. You can skip that if you don't want to actually write the values. Don't do B. You don't need to plot the graph. I'm fine for you to not plot it. But what you should be doing is use your calculator to get the linear regression line. So basically these questions, this one and the next one, I think, they assume that you don't know how to do a linear regression and that you're just gonna, plot points on paper and draw random lines. Instead, answer the question, get to the actual meat of what it's asking you, but don't bother with all the drawing of the graphs. Use your calculator and use it to effectively find the model, right? So for each of these questions, use the data, but use an appropriate model, it's given to you here, and find what the parameters of that model are. So basically, find me what capital A is and find me what little b is. Okay, and then once you've done that, do part D. Okay, so that's it. Give that a go. Find A, find B, and then answer part D. You can pause. Okay, and then this is a question about the population of the country of Mozambique. You can forget A, unless you want to write out the values. Quickly do B. Don't worry about C. And for D, effectively just find A and B. Right, so I just want to know what is this and what is this. Okay, the A and the B and the T. I'll rub that out so you can see it. And then, yeah, do answer E. Okay, so similar to before, but this time you're using, I think this one's the other type of model. So give it a go. And then you've got one more question, which is one I quite like, actually. So you can pause. Okay, so this one's quite a bit of fun because it's not really trying to hold your hand and tell you how you should be coding the data, whether or not you're going to plot things or not. So I quite like this question, and it's quite a real world sort of problem in that you've been given some data and someone comes along and says, explain this data to me. What is the relationship? Maybe you can even make some predictions, right? So here is the data. You've got 4 sets of data points. To be fair, not that many. In the real world, you would never really base a pattern off just 4 data points. But obviously, too many data points, this question becomes a bit too difficult. So see if you can figure it out. You've got 2 cases to work with. We can rule out it being a straight line quite quickly. So try either of these and see if you can figure out what the best relationship, that you can come up with is, and then see if it agrees with what the book tells you. So give that one a go. It's quite a nice one. You can pause the video now.